So we've learned the right-hand rule for force, and it is very useful, but it doesn't stand alone, because the right-hand rule for force will only tell us the direction of the force, but it will not tell us the strength of the force or the magnitude of the force. So we need an equation which will tell us that. Now this equation is on page 778, and this is equation, let's see, it is equation 24.5. Equation 24.5 on page 778. Now, unfortunately, this is one of these that takes two forms. It looks different in the book than it does on the AP gouge, so let's go with it here. In the book, it goes F is equal to Q V beta sine alpha. Okay. AP, which is the one that we prefer, goes with the F of m, that's the force of the magnetic field, applied by the magnetic field, is Q V sine theta beta. Now what do all these mean? And you'll see the parallels between them. The F is magnetic force, and that's going to be in newtons. Q is the charge that is moving through the magnetic field, and that's going to be measured in coulombs. V is the speed of the charge, and that's going to be in meters per second. Speed of the charge in meters per second. Beta is the strength of the magnetic field, and the units for that are teslas. I don't remember if we mentioned that last time or not, but the magnetic field, the units of magnetic field is in teslas. We named him after a pretty cool guy, so there we are. Now, this theta is the angle between the velocity vector and the magnetic field vector. So it's the angle between velocity vector and the mag field vector. And that's going to be in degrees. Okay, and when you're doing your right-hand rule, it's the angle between the thumb and the forefinger. So if the thumb and the forefinger are at 90 degrees, you get full force, and if it's less than that, you get less than that, less than full force. And if they're truly parallel, the magnetic field and the velocity vector going truly parallel, then there is no force whatsoever, because the sign of 0 is 0. Okay. Let's see. Now, suppose we have a proton that is being expelled from the sun. So it's going to be a proton in the solar wind, and we're going to say that it's going 5 times 10 to the 5th meters per second. And we're going to say that it encounters the Earth. Here's the Earth, and there's magnetic field lines coming out like this. And we're going to say that it encounters the Earth, our proton, right at the equator, so that the angle between the velocity of the proton and the magnetic field line is 90 degrees. Okay, so theta is going to be 90 degrees. It's going to hit right along the equator there. Let's see, the force of Earth's magnetic field is accepted to be 5.0 times 10 to the minus 5th teslas. Okay, that's a real number. Let's see, is that all we need? Yeah, I think so. We want to find the force on the proton. Force on the proton. Okay, so let's look at this. This, by the way, is an example problem on page 779. So this is on page 779. So we're going to use our equation, our AP version of the equation here. So we're going to calculate the force from the magnetic field. The charge on a proton is the elemental charge, 1.6 times 10 to the minus 19th coulombs. I get that off the AP gouge. Remember, the charge for a proton is the same as the charge for an electron. We're going to multiply that by the velocity of the proton. Oh yeah, I guess I didn't mention that one over here. Let's see, the velocity was 5 times 10 to the 5th meters per second. And that's a fairly realistic number. Oh yeah, I did say that. 5 times 10 to the 5th. It's getting late, sorry. Okay, anyway, 5 times 10 to the 5th. Now, the angle is 90 degrees, so it's going to be times sine of 90 degrees, which is 1. And then we're going to multiply that by the strength of the magnetic field, which is 5 times 10 to the minus 5th teslas. Grind it all through the calculator, and it comes out to be the force, the magnetic force, is equal to about 4 times 10 to the minus 18th newtons. That's the force. Now, that seems like an extraordinarily small force, and it is, but we have to keep in mind that protons are really, really, really light. I think it's 1.67 times 10 to the minus 27th kilograms is the mass of a proton. So in comparison to how many kilograms, this is actually a gigantic force. And this is going to shove that proton a lot. It turns out that elementary particles, protons and electrons, they get shoved around and accelerated gigantically by some pretty insignificant magnetic fields. This one, I think the book comes out to be 200 million Gs. For this force acting on a proton. So yeah, it really it sends it away from Earth. This is how Earth's magnetic field is able to protect us from the solar wind, because it just obliterates any proton, any charged particle that is coming at it from the sun. It just completely deflects it, channels it into the, they wind up following the magnetic field lines down and crashing into the atmosphere at the north or south pole. And that's actually how we make the northern or southern lights. Okay, so let's imagine that for a moment. Suppose instead of coming in nice neatly at the equator, what if the particle came in north a little bit at a place where this is only like 45 degrees? So this angle is 45 degrees. How would we handle that? Well, it's not complicated at all. The only thing that changes is the sign of this angle. All the other information stays the same. The field strength is the same, the charge on the proton is the same, the speed is the same. So the only thing that would be different, this would be sine of 45 degrees, which I think is 0.707. So it would be about 3/4 of this, so you'd wind up with like roughly 3 times 10 to the minus 18th newtons. So a little less force, but it would still deflect it. It would still carry it away from the Earth, protect the atmosphere. So yeah, that's mathematically it's not that complicated for us to handle an angle. However, it turns out that AP2 doesn't want us to worry about these angles. All that AP2 worries about is if the angle between the velocity and the magnetic field is 0 degrees or 90 degrees or 180 degrees. Or possibly 270 degrees, but I'm not sure about that. But it doesn't matter anyway. So basically, it's where the sine theta is 0 or 1 or 0, and they really don't want you to don't care if you know how to handle it on these intermediate angles. Now, why is that? Because it appears it's a trivially simple thing. But when you think about it, if the particle does come in at an angle like this, it's going to start following kind of a spiral path down the magnetic field line. They explain this pretty well. Let's see, on page, where is that? Yeah, it's on page 781. Page 781, they explain this. Yeah, it's going to follow a rather complicated path down the field line, and the angle is going to be continuously changing. And by continuously, I mean like in a regular, predictable way. So you can actually calculate the changing directions and changing accelerations if you use calculus, but we don't use calculus, so AP2 only wants us to know the simplest versions here. So 0 degrees, 90 degrees, 180 degrees. So if the angle between the magnetic field and the velocity is perpendicular or parallel or directly opposite, you have to be able to handle that. There are some good conceptual questions that come in with that as well. But that's all we have. So we've learned about how magnetic fields will exert forces on individual moving charges. But what if you have a whole bunch of charges, like a whole bunch of charges going through a single wire? So it seems that a magnetic field should be able to exert a force on a conducting wire. And if we are ever able to get back in the classroom, I'll let you do this lab where you run a current through a wire in a magnetic field and see if you can make the wire move. And it's kind of interesting. So anyway, to make sense of this, it's useful, I think, to step back a little bit and look at how bar magnets behave, and that will help you analyze or predict how magnetic fields around wires will interact with fields, just ambient fields. So let's first look at a couple bar magnets here. So we're going to put two bar magnets side by side, and we're going to put them north pole to north pole and south pole to south pole. Okay. Now we know that these magnets are going to repel each other just from our experience, but how does this look in terms of the fields? Now remember, we have magnetic fields that emerge from the North Pole, re-enter the South Pole, like so, and from the North Pole and re-enter the South Pole. That's the direction of the magnetic fields, and obviously there's field lines over on this side too, but we're not so worried about the ones on the opposite sides. What we're concerned about is the fields here in between. So what we have is two magnetic fields that are running the same direction and parallel to each other. So same direction. The fields are running the same direction and they're parallel. And we have a repulsive force. They repel. Okay, so we have forces that run like this. Now, conversely, if we have our two bar magnets and we lay them north-south, south-north, we know from experience that these things are going to attract each other. Now, how do the fields look? We have field coming out of the north into the south, like so, and out of the north and into the south, running this direction. So here we have the magnetic field lines running parallel to each other, but they are in opposite directions. The magnetic fields point in opposite directions, and they attract. Right? So most of us can, and they, yes, so they're attracting each other. The magnets are attracting each other. Most of us can remember this just by visualizing it without even writing it down, but if writing it down will help you, then by all means do it. I'm talking about like on an AP exam or something like that. But it is useful to make a diagram like this for these problems that we're going to be doing as we move forward here.